I want to talk about sorting manure and minimizing the mess in terms of how do you approach it really from a systems perspective. What are some things that are going to get you in trouble? I'm not going to get into specifics of all of the different equipment and companies here. I want to talk about it for me. If you think you have life rough and a boring job, I think that would be the ultimate of difficult jobs to do, is just sit there all day and wait for that cow to poop. And one bucket's for urine and one's for feces. So you just sit there and wait, and then that's your daily job. So hopefully your career path is a little more challenging and exciting than that. Well, about everybody can do an assessment. Assessment is just simply an evaluation of what's going on. And you can look at something, you can walk onto a farm, and you can say, yes, no, it's working. Okay? The difficulty is not everybody can understand why is it successful. Or is the dairy really accomplishing what was originally proposed? And that's really what we want to look at here today. Hopefully, when you leave here, you'll have an understanding of what it takes to make a successful system here. And so in terms of minimizing the mess, I found this definition of a mess. It's a disorderly or a confused collection or mass of things. And I'm going to show you some pictures of some disorderly or confused mass of collection of things. But a lot of dairies we walk onto, that's exactly what we see. We see a lot of components that are mismatched in capacity. We see components that may or may not be working. We see a lack of commitment to operation. We just see basically what we're talking about here. And so when we talk about minimizing the mess, what we're really talking about here is the system approach. And it's got to work for your particular farm. You just can't, it's going to be variable for each farm. So I broke this presentation down into species. I'm going to talk about feed and farming, excretion and extra water, components and commitment, equipment and engineering, and serviceable and sensible. And so that's where we're going to try to take this presentation together. First, we're going to talk about from the feed side. And I apologize to the international community here. I'm going to be using English units here. But the National Research Council has dietary recommendations in terms of phosphorus. And really, when we start talking about manure management, when we start talking about minimizing the mess, it's going to start with nutrition. You can begin to, anytime we start looking at developing a plan, anytime we begin to start talking about working with the dairy, what we really want to start with is the feed, because the feed input is going to ultimately drive what happens on this dairy. You can look here at phosphorus at 0.4%. Phosphorus up to 0.55, maximum herd size on 100 acres. If I'm in a 50-50 crop rotation, if I'm down here, I could milk about 93 cows. If I'm sitting up here, I'd have to reduce it to 60 cows. So this phosphorus issue is a real thing. On the phosphorus issue, what I'm going to tell you is the cheapest diet may no longer be the cheapest diet the way we've traditionally thought about it. The cheapest diet, we're going to have to start thinking about what is it costing in order to get this material land applied. What is it going to cost me in order to accumulate these extra acres, particularly when we start talking about phosphorus. We can look at mixed grains, and the picture gets even worse with the mixed grain. So at 0.4% phosphorus, we're at 73 cows. Basically, that's what this land base, this 100 acres of land base would support. Out here, we're down to less than 50 cows. So this whole issue of phosphorus and what impact it's going to have on the diet is really a critical thing. Just looking at a 2001 study from Pennsylvania in terms of willingness to deal with this phosphorus issue. Nutritionists said yes, 75% of them were willing to reduce phosphorus to the NRC recommendations. That's basically 0.4 is high. The NRC recommendation is going to be somewhere between 0.3 and 0.35. So even at 0.54, we're on the upper end. Dairy producers, basically the attitude is no way. Okay? We're not going to reduce phosphorus in terms of that's currently in our diet. Excess P, basically the dairy producers felt there was no excess P in the diet. And yet, that's one of the real problems we're faced with. Looking at a study out of Virginia in terms of what was actually being fed based on 33 dairies in the Shenandoah Valley. Basically, dietary phosphorus as fed, dietary fed here was 0.5. That was the mean. Okay, that was the average. 0.34 was actually what was being required. Percent excess, 45. There was one dairy that was underfeeding. There's one dairy sitting out here at 0.65, had basically 125% excess phosphorus in the diet. What did it look like? This is kind of an interesting slide, because every pound of phosphorus basically that was brought onto the farm in terms of the feed ingredient was excreted. If you look at the numbers here, this is what was purchased, this is what was excreted. So when we start bringing phosphorus onto the farm, there's a high probability, there's a high probability that we're going to have to deal with it on the excreted mode. So we're going to say that first we're going to start with the feed in terms of sorting through this, minimizing this mess. We look at these nutrient management plans that are being required. Basically all the nutrient management plan is, in simplistic terms, it's just a scale. We're going to balance what the agronomic requirements are with the animal. So we got to know what the crop requirements are, what the diet is, and then we got to look at what's available. And so it's just a balancing act when we start looking at nutrient management plans. We're looking at what's excreted and what's basically the crops are going to be used. So when we excrete, for example, excess phosphorus, then we're going to have additional. This just looks at it in terms of some NP and K. These values are relative. But the interesting thing is when we look at manure, basically the nitrogen to phosphorus ratio as excreted is about 2 to 1. By the time we get it to the field, it's probably 1 to 1 as an overall system, just due to the nitrogen losses. And yet the crops themselves, typically the ratio of nitrogen to phosphorus is 3 to 1. So if you've been applying on a nitrogen basis, and you're in sensitive groundwater areas, the real issue is that you've probably been over-applying phosphorus for many years, because typically speaking, phosphorus is a limiting nutrient. It takes about 1/3 as much phosphorus as it does nitrogen in terms of the crop farming practice. This just shows the impact if we're applying it on a nitrogen. If we had 100% available, take about 3.6 acres. If we used 100 pounds per acre, only 25% in the ends available, it's about 0.9. But when we get into this phosphorus base, it really has an impact in terms of the crop acreage requirements. We go from our basically feeding, and now we start looking at some excreted values in terms of what happens with these excreted manures. Well, this is losses. One of the difficulties we have is with these nitrogen, we've got losses everywhere. We've got losses in the building, we've got losses in the storage, we can have losses during application. If we do not get this nitrogen incorporated immediately, we can have some additional losses. So it's real hard in terms of farming practices to come up with an estimate of what's happening to where the nitrogen is. Phosphorus is relatively simple because it's stable, it's going to stay. So if you're not land applying the phosphorus, then it's probably going to be going into the bottom of the lagoon. The best example I know of, we had a situation in Kansas with the dairy where basically they bragged to us that they hadn't applied phosphorus, they hadn't applied or cleaned the lagoon in 10 years. Okay? That sounded great. However, the state came in, made them clean the land, clean the lagoon out, and land apply the manure on a phosphorus basis. They went from needing 180 acres a year to about 1,200 acres. So when you start dealing with phosphorus, the least land base that you will be required is if you deal with that excreted phosphorus on an annual basis. If you let it accumulate, then what you're actually doing is requiring additional land somewhere down the road, particularly if the environmental regulations are limited. In this particular case, they could put on 3 years of phosphorus, and we still require that much extra land. So I'm just saying that this phosphorus issue is real. And you can look here in terms of application methods. Nitrogen, if you don't incorporate, if you do incorporate, but the P-based here basically always requires about twice as much land. Total nitrogen, it's variable by farm. This is one of the difficulties in terms of estimating losses. We can have anywhere, on this particular farm, it was 300 pounds per acre inch up to 700. So this particular dairy right here basically is requiring twice as much land as this particular dairy right here in terms of water and liquid disposal. We look at it on a phosphate basis though. This one's pretty low. Here's 50 pounds per acre inch, or about 65, up to 200. So once again, we see this high variability between farms, even though all of these dairies basically are in the same region, using the same type of nutrition practices. This is just a pictorial thing of what happens with cows. If I only need 3 acres, in other words, if my nutrient management plan says I can basically put the manure from 3 cows on 1 acre, so this is cows per acre. If I'm at 3, I need basically 160 acres for a 1,000 cow dairy complex. If I'm 2, so my nutrient management plan basically says for the manure excreted from 2 cows, I can apply that on 1 acre. I need another quarter or 160 acres of land. However, if it's a 1-to-1 type of ratio, you can see here the additional land base required. Okay? And so when you start working with some of the large dairies, this here, basically the block of land required within the vicinity of that dairy for manure disposal can get quite large. And then when you have competing dairies or competing feedlots, this becomes even more of a challenge to find this land available. And so it does go back. So with feeding and farming, we want to begin with the diet. The diet is going to impact crop acres. Lab analysis, we want to look at our feed, our manure, and our liquid samples, know what we got. And the take-home message here would be is that phosphorus will remain somewhere. Now we look at book values of excreted manure. We can look at the American Society. I still use Ag Engineer, but it's American Society of Agriculture and Biological Engineers now. We can look at Midwest Plan Service. We can look at NRCS. And one of the real challenges we're faced with is Midwest Plan went from 120 to basically 150. ASAE went from 115 to 150. I think NRCS is still using 112. This makes a huge difference. If you had a system designed prior to 2000, you were probably in this 120 to 110. The reality of it is probably even back then the cows were excreting 1/3 more manure than what your system was designed for. And so this plays a real role, particularly for even as some dairies have expanded and just add a few cows each year, the system real quickly becomes undersized, and then it becomes overloaded, and then we have some poor functioning lagoons, and then we're looking at lagoons full of solids. And there's been some other changes in terms of nitrogen and phosphorus productions, but you basically need to be looking at new book values. They now have equations that you can start looking at. You can look at the ASABE standards, so have equations for manure production. Look something like this, depends on where your manure production is. Okay, in terms of pounds per cow per day, it is linear. As the cows produce more milk, you can reduce manure. So one way to basically reduce the manure on your dairy is to produce less milk. Okay, so if you're targeting up here, but you only want to handle the manure down here, just cut your manure production or cut your milk production in half, and that is one viable option. However, when you look at this graph here from Dr. Bill Weiss at the Ohio State University, you will see here, this is pounds of milk per day per pounds of manure per day. Look here at these cows that are 40 pounds or 50 pounds. There are some cows producing 50 pounds of milk that are giving 50 pounds of manure, and there's some that are giving 250 pounds of manure, or 225. And this is one of the great unknowns is you look at this anywhere from about 50 to about 100, 115 pounds of milk per cow per day. Some of those cows are giving 200 pounds of, or producing 200 pounds of manure plus per day. And you've got other cows that are down here around 100 pounds. And so one of the questions now is can you figure out genetically what gene it is that causes these cows here to produce as much manure as these cows back here? That's one of the difficulties when you start talking about book values. Where are the nutrients located? This was a 1939 study. Dr. Deanne Meyer at UC Davis repeated it in 2006. And basically, within the feces and urine, if we separate it, it's about a 50-50 split. Phosphorus, most of it would remain within the solids. And then the potassium, basically, there's really no difference in terms of the location of nutrients in spite of the difference in milk production and manure excretion values. So we can look at it, and it's just basically 50-50 for nitrogen. Phosphorus does remain with the feces, and the potassium basically goes with the liquid. You can look at it on a graphical basis, but it's there. Now you can look at ASABE, when they revised their standard in 2006, they did produce some graphs in terms of giving you an idea of what's going to be the phosphorus excretion based on pounds of milk. They have some more complex equations that you can use as well. And you can also do it for nitrogen, where you can estimate it based on it. And if you use those standardized equations, you get nice straight lines. You can see phosphorus, basically it's going to be somewhere around 0.4. This nitrogen will be somewhere around 1 pound per cow per day, based on about 80 pounds of milk production. Okay. The other, when we start looking at it in terms of an E, is the extra water required? Let's see if this is still working. Sorry. Extra water required is the other one we want to look at. And a lot of times these systems will, every place I've been on, basically, the more water we had, the better the system worked, and yet we're in a conservation mode. And if we take a system where basically we're trying to, say, reclaim sand, or we're trying to recycle water or flush, and we want 1% total solids in the recycled water, but we're dealing with a single-stage lagoon, we've got to add over 200 gallons of water a cow per day to the system. Okay? If we remove 30% of the solids, or at 60% moisture, we're down to about 140. And if we can get 60% of the solids out at a 80% moisture content, we can be down to 80. Now this is all a function of basically what the total solids are in the recycled water, what you feel like you can live with. But what you'll see here is that if you're dealing with a single stage type system and you're requiring recycled water, basically in a single stage system that's going to be at somewhere between 7 and 15%. It's going to take a lot of extra water in this system. And where that really starts coming into play was when we start looking at gallons. So this is just a 500 cow dairy. If we do not remove any solids, we get about 3.1 million gallons of manure. It's going to take about 41 million gallons of water to get it down to 1%. Okay? And this is going to come back a little bit later when we start talking about system operation. And you can see here, if we can live with 3%, so the more solids we can get out front, the more solid separation we can do, the better job we can do there. Ultimately, the less water that we're going to have to deal with. And so your daily disposal costs can range anywhere from $2.20 just to get rid of water, down to about 18 cents, depending on the type of system you selected. And so this is a real critical factor when we start looking at how we design these systems, is are you committed to dealing with the extra water? Particularly if there's rinse water, if there's clean water, if there's a fresh water cycle, are you really committed to doing it? We've been involved with some dairy projects recently where basically the decision was we can't get rid of water. And so they changed the whole plan once they began to look at exactly the quantities of water required. So you can do the math. You can take 80 pounds of milk, you're going to get 147 to 150 pounds of manure. You'll get about 5 gallons out of the parlor. You might have 10 gallons of rainwater falling on the surface. So for every truckload of milk you ship, you better plan on dealing with 4 truckloads of manure. Okay? So that's the take-home message is it's not for every truckload of milk I ship, I've got a half a load. Somewhere along in this equation, it can range 3.5, might get as low as a 2.5, 2 to 1 on a good scrape dairy. But there is a lot of extra water basically being required for a lot of systems. So this is the problem we're dealing with, is this ratio here just of the milk to there. So I'm going to tell you to use 21st century excretion values. If in doubt, make sure that your design engineer uses at least 150 pounds. Okay? Extra water can range anywhere from a good scrape dairy might be down as low as 2 or 3 gallons per cow per day. If you've got sprinkler systems in there, if you've got clean water cycles in there, it can be up to 60 gallons a day. And that's all going to be a function of the system that's designed. If someone tells you that it takes 1 gallon of water, I just use 3 to 4 times as much, because it seems like that we do tend to use more water than there. So be aware of disposal costs, particularly if you start talking about, I want to install a sand recycle system. That sand recycle system, no matter what kind it is, will require some additional water, and in that additional water, that means there's going to be some additional hauling and pumping costs. And then basically, if you reduce water usage, you're probably going to reduce the equipment efficiency. So when you make, and we'll talk about that here in just a minute. Components, these things have to work together, okay? A system is just a collection of organized things, might be interactive, interrelated, and interdependent, okay? And I'm going to probably tell you up front that maybe I'm biased, but I think you need to hire some high-quality engineers involved with the project to make sure that this all functions together. We'll talk about that in just a minute. One of the big things we see in terms of components not functioning, particularly when we get into retrofit types of things, is many of you will leave here with in mind in terms of, I'm going to purchase this piece of equipment. Well, the question I'm going to ask you is what's the flow through that equipment compared to the volume you're dealing with on your particular dairy. If I've got an equipment capacity that will only handle 200 gallons a minute, then, and I've got a flume, for example, at 1,000 gallons a minute, I cannot pump it more than 12 minutes an hour. If I do, I've exceeded the capacity of the equipment. And anytime we have to place storage structures between two pieces of equipment, basically it's because we've got mismatched components. We've got things that are not working. But in that storage structure, we need to make sure over a 24-hour period that it's completely empty, unless it's a final stage type lagoon. And so this is a real deal here in terms of dealing with. I was involved with one dairy. They were having all kinds of trouble, and basically they were running a pump 2,000 gallons a minute for 20 minutes every hour. That was about 24,000 gallons, and the equipment could only handle 12,000 gallons a minute. And what they failed to understand was the initial plan was they either had to put in, they were supposed to put in 2 separators, and they only put in 1. And so as a result of that, pipes filled with sand, there was just all kinds of problems with flow. And so when you have these mismatched components, you will begin to have problems, okay? Understand solid separation. This cow's going to produce 150 pounds at 87% moisture. That'll be about 20 pounds of solids. You could dry it all out. It's about 130 pounds of liquid. If you've got a separator that only removes 20% of the total solids and it's at 20% moisture or 60% moisture, that's where it's nice and stackable. That's what everybody likes to handle. It only results in about 10 pounds removed. There's still 140 pounds going to the lagoon. Okay? So these numbers, you can play with the numbers all you want. Okay? But the bottom line, if I've got a separator that's only performing at this level, basically I've still got a size of lagoon the same as if it was there or if it was not. Okay? At 60% removal, 80% moisture, then you're at about a 60-90 type split. So the separator efficiency, separator performance is going to be really critical in terms of how you make this thing work. Okay? We take sand-laden manure systems. Okay? They're complex types of systems. Basically, we're trying to go from a manure slurry to a clean sand in about 20 seconds. And so in order to accomplish that, no matter what type of system you're using, it's going to take a system that's going to flow together. We're going to have pump capacities. We're going to have everything working together to make this system go. And the challenge with sand is really once it's in suspension, you want to keep it there. If you slow it down, the sand will settle. Okay? Makes no difference what type of system you have. And when you start dealing with sand-laden manure, when you start dealing with sand recovery, if you cannot mimic nature, if you cannot mimic what's happening in a stream, I tell everybody go fishing. Okay? Look at what's happening on the stream banks. Where's sand settling? Where's it picking up? Where's it? And the same thing is going to happen in terms of dealing with this sand-laden manure. You also have to have a commitment to the operational procedures. When you buy that piece of equipment, you are saying that until I take that piece of equipment out, I will operate it according to the manufacturer's recommendation. And if you're not making that kind of commitment to the system, then it's not going to perform, and the overall system will give you trouble. You're going to have nothing but difficulties and dissatisfactions. So you have to make sure that you're committed to the water flow, agitation times, maintenance schedules. If you've got 10 motors there and they require daily maintenance, you're making that commitment. Okay? Or pumps, or whatever types of systems it require. In terms of agitation, the same thing goes. If you change bedding, then you may change the overall system performance. So, and where commitment really comes in is most all of the equipment will have a daily rinse schedule where the screens have to be washed, or there's some process in there in terms of just plating the crud out. I'll use that word, I reckon. And so when you make that commitment, that's where it comes into play. So somebody has to maintain this system. It might look good on paper, but somebody does have to know how it all operates. Or you have to be willing to climb off of this diving board. You like to climb out here, have to climb up here. If you miss a step, it's a 10-foot fall, but don't worry, this is what you'll land in. Okay? So, I'm just saying that when this system's put in, there's got to be some kind of thought in terms of how am I committed to maintaining it according to the manufacturer's recommendations. Okay? So, is service available? If equipment goes down, and this is something we don't think about, but if equipment goes down, basically for every day the equipment's down, we've got to add probably 2 or 3 times as much water in order to dilute back to the desired moisture content in that lagoon, particularly when we're using recycled water. So, if you have things occurring like this, and you let those go for a couple of weeks and solids pass through, there will be problems. So components and commitment, I'm going to say they're going to make up the system. If you got mismatched components, you're going to have problems. So if you're doing a retrofit system, you really need to do a flow diagram. How much is coming out of the barn? What's the flow rate for this piece of equipment? And you need to flow this whole thing out in terms of a gallon per minute or gallon per hour. But you really got to make sure that you understand how that is. Storage structures are used to match capacity of components. If at all possible, I like to eliminate storage structures, but it's not always possible. And really, equipment performance is really proportional to your commitment to operating it according to the rack. In terms of engineering and equipment, it's a complex system anymore. Okay? No matter how you sort through this diagram here to try to get from here down to here, this being basically manure, this down here being land application of, you've got all kinds of decisions that have to be made in regards to odor. What type of bedding am I going to use? Am I going to recycle? Am I going to use solids? You know, and even now you could throw another level of decision in here. Am I going to produce energy? Okay? And so this is just the types of things that hopefully you can come. So it's one of the things that's real interesting. I think this was one that John here was involved with in terms of a digester. Designed the system during construction. It was modified. Okay, they basically forgot to put the insulation around the perimeter of it, and it never performed. So it was an expense, but for some reason somebody made this decision at midstream of construction to basically take it out. Not the engineer's fault, but you've got to be asking these questions. If we modify something at midstream, what happens upstream? What's going to impact performance upstream? And it's going to impact performance downstream. And in this particular case here, the gas production was not quite as high as originally intended. And so we've got to be asking these questions. And one of the things that we see oftentimes happening is the system will be designed, but then during the construction process, somebody decides that they can do it better without fully understanding the overall system and why it was that way. Not saying that they can't always do it better, but it is something there. And so you really got to ask when you start making these modifications, why was it designed this way to start? Okay. One of the hardest things that I know the engineering community has is trying to get valuable information in terms of inputs and outputs. It's just this whole thing in terms of how much water is really required for this piece of equipment. We're talking recycled water, so we're talking water that might be able to come back from the lagoon. What total solids content can we deal with? What about the clean water? How much extra water? It's really hard to get this type of viable information. But you do want to ask questions. This is a good example of one. Well, it was taken onto this particular site, basically, in order, they were promoting the aeration systems. I'm not bad-mouthing the aeration systems here, but whoops, they had a nice red lagoon here and asked a basic question. How much water a year are you using? And he said, what? I said, well, how much water is coming into the system? He said, well, you see this pipe right here? This is the irrigation canal coming around. All of the water used to irrigate these trees back here comes into this lagoon and then gets pumped out. That was over 200 gallons a day entering the lagoon just out of this irrigation canal. I can produce a red lagoon with 200 gallons a day without any additional equipment. Okay? What the old engineers will tell you was called an anaerobic lagoon. Took a lot of extra water to do. So the question now is it really the aerators that's a result of this, or is it the fact that there's 200 gallons of cal a day coming into this system? Okay? So you want to ask questions to make sure that what you're seeing is going to match up with your particular dairy in the way you're willing to manage it. You can use slurry stored, you know. If you've got to minimize water, and if you're in a situation where it's hard to irrigate, then maybe this is a route to go. You can start looking at some different equipment in terms of performance. This is old data. I realize that all the equipment now has been new. But you start looking at total solids removed. Basically, 10 to 20%, 10 to 30% is the range in which we're typically dealing with. We look at solid separation equipment. You can go into stationary roller press extrusion type units, non-mechanicals basically, weak walls, trenches, or small lagoons. In 2002, probably one of the most comprehensive studies was done. Ford and Fleming, I think they were out of Canada, looked at all of the research available, peer-reviewed, published research available in terms of separator equipment, and there were only 27 studies. Okay, and basically when you start looking at energy requirements, when you start looking at throughput, of these 27, even 6 of them did not have hourly capacities of the equipment themselves. So you can look at different types of equipment in terms of screens, in terms of performance there. You need to be thinking about, if my regulations require 180 days of storage, then I may need to have a fairly large concrete area here in order to provide storage, adequate storage space of that equipment. You got to think about operation, think about daily maintenance, just in terms of commitment. There's the fans unit, there's the Benson unit. The Benson unit I know was tested at there's an international testing facility where they will actually measure throughput and equipment performance. I think Benson was one of the few that was tested there, but the extrusion type things. One of the real challenges with the mechanical systems is screen size. Typically they're going to be 500 to 1500 microns. 64% of the solids are less than or equal to 500 microns in size. Okay? So when you look at some work by Deanne Meyer that she did in 2006, where she took feces samples and began to separate them into particle size, 50% of what was excreted was less than 125 microns in size. And yet we've got screens that are dealing with 500 to 1500 microns in size. And you can see here, so this level here, about 58%. If you add this in, you got 64%. It's at 500 microns or size or smaller. So typically what we're seeing is a lot of the systems we're really only touching some of these larger particle sizes that we're dealing with here. This is just a fairly simple system. It's just a concrete base and scrape. Forget sand recovery. They didn't have a lot of extra land in terms of disposal water. Wanted to use sand. Basically just pushed it out and go in and clean it out once a year. There's just pictures of the wheat wall. There's a small one in Pennsylvania, one in Ohio. And performance, typically, we do see in terms of total solids removal. Deanne Meyer has published a 2004 peer-reviewed journal article on the performance of them. So with engineering, we need clear objectives. It's got to be a systems approach. You have to have some kind of flow diagram. How's this material moving through this system? What is going to be the rate? And what's going to be our end product down here? And one of the real questions we've got to be continually asking is water quantity, water quality, and ultimately disposal situations. When we have a situation like this, we're probably going to have trouble. We don't have a crust. We've got a few solids on there that move across the surface, and that's really when we begin to see odors and neighbors complaining. This is one that, right there is a fairly nice house. Unfortunately, that's Mom's house. So they were able to get by placing this particular base in there, but those are types of things that you want to watch out for. When we start talking about reclaiming sand, I'll just comment there, the more water the better. One website says 1% total solids into recycled water. One says 3 is probably realistic. When we get up to 5, we're in trouble. We can look at rainwater. We can look at roof water, extraneous drainage, pasture ponds. I mean, we can look at a lot of different places to get this water. And some of these systems, to get to 1% solids, you may have to be adding 40 to 50 gallons more water per cow per day to the system. And so we do have to deal with it. Different types of systems out there. For example, this is McClanahan, this is Parkson. There's the sand trap, another sand trap, sand lanes. And then for smaller dairies, and we've even worked we worked with one 3,000 cow dairy that said, we're not going to recycle sand. That might sound harsh to some of you, but when they looked at the cost of getting rid of water, they looked at the availability of sand, the cost of getting rid of water, the cost of all of the equipment and the pumps and the process and everything. They said it'd be a whole lot cheaper if we did not recycle sand. This is just a simple single row dairy. This is the cow housing area with 3 stalls here. So you see here, this bay right here is actually used to stack some sand in. They scrape the manure off, So this part right here, scrapes manure into a basin. We have a woven wire flooring gate here so that the liquid drains out across the vegetative filter. So there are some simple systems out there, you know, that are fairly easy to do a flow diagram. It comes here, settles solids out, settles sand out, liquid drains across the vegetative filter. So equipment, understand capacity. If you cut corners, you're going to probably cut performance. I'm going to tell you to ask for independent evaluations. I'll probably get in trouble here with this statement, but if the dairy industry required the same level of independent research studies and documentations be available prior to purchasing manure processing equipment as you require the feed industry, there would not be any products on the market today. Okay? Feed decisions are based on research. Manure decisions are based on testimonies. And that's one of the big challenges in trying to get information. Okay? Beware if it works with municipalities. And the reason is, I'm not saying it won't work with the dairy, but a municipality can always raise taxes to cover the cost of the system. Now, you may be a unique dairy producer that you can raise your asking price for your milk. I haven't met too many of those yet. But you have no way of guaranteeing 5 years from now that whatever you're doing, you can still afford to pay for it. And there is a major difference. I've worked with a company there in Manhattan, Kansas, that has been doing municipal treatment systems since 1970. 2 years ago, they made the decision they were going to get into manure processing on dairies. After $500,000, they said, we can't do it. They said, we cannot meet quality standards that are demanded by the regulators. They came up with a piece of equipment that worked great. I asked them one simple question. What's the flow rate? We can handle 40 gallons a minute. And I'm going to send 2,000 gallons a minute at it. So they backed out. So I'm not saying that it's not possible, but I'm saying you want to do your research, because time and time again, we've seen that type of equipment come on, and when you start adding chemicals and those types of things to the system, okay, those costs begin to increase over time, and that's where this commitment comes in. So you just have to ask yourself some additional questions there. We're going to wrap up here with serviceable and sensible. Just kind of a list of things there in terms of making it work. Talk about serviceable. This was a dairy project. This is at my alma mater, Virginia Tech. They told me separation didn't work, but they put in these separation basins at the end of their mechanical separation system. But it doesn't work. Well, it isn't going to work. There's no way to clean them out. Okay? So pretty well guaranteed that if you have no way to clean out these basins, that it will not work. Okay? So got built-in obsolescence there. Estimate operating cost. It's nothing magical about estimating operating costs. Look at the total horsepower. You got 7 boxes there, 7 motor starters there. Take the total horsepower times 0.75 times what you're paying for electricity times the hour per day. Figure out what it's going to cost. 20 horsepower running 10 hours a day is $7.50 per day operating cost. So make sure you know what those things are. I came up with this little chart. This is dangerous, but you know, years of schooling here, serviceable, sensible. So if a kindergarten can run it, you're going to be very satisfied. Okay? If it requires a bunch of doctorate people to run it, forget it. Okay? And so with that, we'll try to take any questions.